All right, so let's look at some questions from the Module 5, Lesson 4 problem set. This lesson's all about calculating theoretical probability. So what we've been doing before is like running trials of things, right? Looking at numbers of observations and then making estimated probabilities from that. Now, instead, we're going to look at, can we calculate what the probability of something should be theoretically without having to like do any trials or any experiments. And the way you calculate that is the probability of a given, I really feel like they should put outcome here instead of, well, okay, so they're saying an event is a collection of outcomes. I don't know. I think me and the book kind of disagree on the way the words outcome and event should be used, but whatever. The probability of the event being a collection of outcomes, according to the book, is the number of favorable outcomes. I prefer the word desired outcomes. It means literally the same thing, divided by the number of possible outcomes. What that really means is you take the number of ways the thing you want to have happen could happen, divided by the total number of ways the thing you're doing could turn out. So, for example, if I was looking at this spinner and my desired outcomes were purple and green, then the theoretical probability would be 2, because there's 2 ways I could get that. I could get a purple or a green, divided by the total number of ways this spinner could turn out, which are 6. There's 6 different spaces. So the probability of purple or green is 2 out of 6, or 1/3, or 0.3 repeating probability. All right, so let's do some of these. It says, in a 7th grade class of 28 students, there are 16 girls and 12 boys. If one student is randomly chosen to win a prize, what is the probability that a girl is chosen? So there are 16 girls. So in this case, the girls would be our favorable or desired outcomes, just because that's the thing that the question's asking us about. And the total number of possible outcomes is not the 12. A lot of students make this mistake of giving me an answer of like 16 divided by 12. The total number of possible outcomes is all the students in the class. So 16 plus 12 is 28. So the probability that a girl should be chosen is 16 out of 28, or 16/28. You could simplify that down or write it as a decimal or whatever if you want. Number 2, it says an experiment consists of spinning the spinner once. All right, and here's our spinner over here, 1, 2, 3, 4, 1, 2, 1, 3. Find the probability of landing on a 2. So in this case, landing on a 2 is our favorable or desired outcome, and we just have to take the number of ways that could happen, which is, I see 1, 2. I see two spaces, divided by the total number of spaces, which is 8. So this is going to be 2/8, which equals 1/4, which is the same as 0.25. I prefer our probabilities in decimals when we can manage. Find the probability of landing on a 1. So this time, landing on a 1 is our desired or favorable outcome. We've got 1, 2, 3 spaces that could produce that outcome. So it's 3 out of 8, or 3/8. Is landing in each section of the spinner equally likely to occur? I would say yes. I don't think there's any reason why landing here would be more likely than landing here, unless you're one of those people that wants to talk about, well, what if the thing's not perfectly flat, or what if the plastic is designed so that it's weighted? Yeah, whatever. If you want to talk about that, go ahead. I say they're all equal. All right. An experiment consists of randomly picking a square section from this board shown below. Find the probability of choosing a triangle. That's just going to be the number of triangle spaces divided by the total number of spaces. Find the probability of choosing a star. That's number of star spaces divided by total number of spaces. I think you get the idea. I'm going to move on. Number 4 says 7th graders are playing a game where they randomly select 2 integers, 0 through 9. So they pick a number like 4, and then they pick another number, let's say 7, to form a 2-digit number. So the number I would have just formed was 47 from my 4 and 7. The same integer might be selected twice, so you could have 4 and 4 and make 44. It says list the sample space for this chance experiment. So the sample space of an experiment is every single possible outcome it could produce, every single way it could go. So if you were to list this, it'd be a pretty long list, because you would have to list 0, 0 is a possible outcome, then 0, 1, and then 0, 2, and then 0, 3, and 0, 4, and etc. all the way up to 99. We're not going to actually list that out one by one. We're just going to write that the sample space is 0, 0 to 99. All the numbers in there, each number in there from 0 to 99 is a possible outcome. And that's what sample space means, all the possible outcomes. What is the probability that the number formed is between 90 and 99 inclusive? That means when they say between 90 and 99 inclusive, it means you count 90 and you count 99 as well. So, well, how many numbers is that? I'm going to be perfectly honest. Sometimes I mess this up. I'm not sure if that's 9 or 10 numbers. I think it's 10 numbers, but let's just be sure. 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. Yeah, so it's 10 numbers. So that's 10 possible outcomes out of, so this is 100 outcomes, right? If it was 1 to 99, that'd be 99 numbers. You throw on that 0, this makes it actually 100 numbers. So this is 10 outcomes out of 100 possible outcomes. That's the same as 1/10, which is the same as 0.1. So there's a 0.1 probability of getting a number 90 to 99 inclusive. All right, what is the probability that the number formed is evenly divisible by 5? So you just got to count all the multiples of 5, including 0, because 0 is evenly divisible by any number. So 0, 5, 10, 15, 20, 25, all the way up to 95. However many of those there are, it's that out of 100, so that's your probability. What is the probability that the number formed is a factor out of 64? So you got to figure out all the factors of 64. That's all the numbers that multiply to 64. We haven't done these this year, but you can make one of these trees where you go, okay, well, 64, you could get 64 by doing 32 times 2. And then 2 is a prime number, so you stop there. It doesn't have any factors like, inside of it. But 32, you can get there by doing 16 times 2. And then 16, you can get that by doing 8 times 2. And 8, you can get that by doing 4 times 2. And 4, you can get that by doing 2 times 2. So these are all the different factors. 2, 4, 8, 16, 32. 64 is also a factor. 1 is also a factor of every single number. So maybe I should write 1 and 2 here or something. So count up all these different factors. Don't repeat count the 2's. You don't get a bunch of 2's. You get a 1, a 2, a 4, 8, 16, 32, 64. And then that number divided by 100. All right. Maybe I'll talk about one more before I cut this off. Okay, so yeah, let's talk about number 5. It says a chance experiment consists of flipping a coin and rolling a number cube with the numbers 1 through 6 on the faces. That's just a fancy way of saying a die. So the experiment, each observation or each trial is 2 things. They flip the coin, then they roll the die. That's one trial or one observation. So list the sample space of this chance experiment. So you have to think about all the different ways it could go. So when you're flipping the coin, the first thing you're going to get is either a heads or a tails. Let's list out all the possible things that could happen just when you get a heads. So let's just note that with an H. You could get H1, that's if you get a heads and then roll a 1. H2, that's if you get a heads and then roll a 2. H3, H4, H5, and H6. That's all the possible things that could happen if you flip a heads first. And then the tails is just going to be the same thing. You could get tails in a 1, tails in a 2, tails in a 3. So you should have T1, T2, T3, all the way up to T6 on there. So that should make 12 possible outcomes. And it says, list the probability for each outcome in the sample space. Well, there's 12 outcomes, and they're all equally likely. I don't think one is going to happen any more often than the other, so they should each just be 1 out of 12, or 1/12. And so then it says, what is the probability of getting a heads on the coin and a number 3 on the number cube? That's this outcome here. Let me list all the other ones just so I have them. T1, T2, T3, T4, T5, T6. Well, heads on the coin and 3 on the cube, that's just 1 out of the 12 outcomes, so it's 1/12. What is the probability? I'm looking at C now. what is the probability of getting a tails on the coin and an even number on the cube? So a tails on the coin and an even number. That would be like tails 2, tails 4, and tails 6. That's 3 desired or favorable outcomes out of the 12 possible outcomes. So that one's going to be a 3/12 probability, and you could simplify that to 1/4, 0.25. All right, so number 6 is sort of the same way. You've got this chance experiment that has 2 parts. First, they spin this spinner, and then they spin that spinner, and you have to start by listing out the sample space. So like you could get red, 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 green, red, yellow, blue, red, blue, green, blue, yellow. I see 6 possible outcomes. So you got to list those out, and then that should help you answer questions A, B, and C after you list it out, and then you can just sort of pick out what you need based on the questions the same way we did here. All right.